Hello there, and welcome to Fall Asleep to Astronomy. I'm glad you've drifted into this little corner of the night with me. Outside, the sky goes on as it always does, stars turning quietly above a world full of questions we still haven't answered. Tonight, we're going to follow one of the strangest of those questions, an interstellar visitor called 3I Atlas, and the way NASA watched, waited, and shared its images with the world. Some people wonder why those pictures came so late, whether the story we were given was the whole truth or just the safest version to tell. We won't rush toward judgment. We'll move slowly, tracing what we know, what we don't, and why this icy traveler stirred so much doubt and curiosity at once. If this kind of gentle, starlit wondering keeps you company, a quiet like and a soft subscribe help others find their way here too. For now, let the questions sit beside you like distant lights, and we'll wander toward them together, unhurried and calm. Now that NASA has finally opened the vault and shown the high-resolution images of 3I Atlas, the story around them feels a little different than it did in those long days of waiting. While you lie here in the dark, that press conference is already in the past, carefully chosen frames on big screens, practiced voices repeating familiar phrases, a firm reassurance that this visitor is natural, a comet, nothing more. The pictures have arrived, but the narrative they were wrapped in is still worth looking at gently from a little distance. Not so long ago, at the Mars Biosignature briefing, you could hear how that narrative was being tuned in advance. Speaker after speaker leaned on the same word, transparency. They talked about never sitting on possible signs of life, about releasing data to the scientific community as soon as it appeared. The phrasing was careful, immediate release, open to scrutiny, nothing held back. It sounded less like casual conversation and more like lines rehearsed until they felt smooth on the tongue. NASA wasn't just explaining science. It was shaping an image of itself, the agency that rushes discoveries into the light, the one you're meant to trust without hesitation. Nikki Fox pushed that image further, describing a pattern. The moment we find something, we put out the images for everyone to see and share. Then came the phrase that lingers even now: we are ultra-transparent. If we had this exciting news and I did not bring it to you, you would say I was hiding things from you. In that single thought, NASA defined hiding in its own words: exciting news held back instead of brought to the public. Later, Lindsay Hayes echoed the same rhythm. We're trying to be very transparent. We announce the signal, we publish the context. The pattern was clear: hint, explanation, branding that sequence as openness. Every spokesperson seemed to hit the same notes with almost mechanical precision. We will be transparent. If we have exciting news, we'll share it. We'll keep telling you what we find, what we see, what we think. Fold that rhetoric gently against what has now happened with 3I Atlas. On the 2nd and 3rd of October, the high-rise camera aboard Mars Reconnaissance Orbiter turned toward this interstellar visitor and took its sharp side-on portraits from tens of millions of kilometers away. Those frames went into NASA's pipeline, and for weeks, the world waited. The shutdown, the procedures, the internal reviews, all of that has already happened, and the images are now public, shown in a November briefing that pulled in pictures from Mars orbit, from space telescopes, from ground-based arrays. The delay is now part of the record, not a looming uncertainty. High-resolution views that could have guided other observers earlier instead arrived as a finished package, narrated and framed. Scientific teams around the world did what they could in the meantime, pointing instruments without the benefit of that early map, That lost coordination can't be reclaimed, even though the images themselves are finally here. Alongside the release, another message was delivered just as clearly. 3I Atlas, NASA says, behaves like a comet. An interstellar comet. Yes, only the third such object we've found, but a comet nevertheless, with a coma, a tail, and activity that, in their telling, can be folded into the family of things we already know. Any talk of alien craft was dismissed firmly as speculation, and outside experts lined up to echo the same conclusion. And yet, around the edges of that reassurance, the object itself has continued to show a personality that isn't entirely tidy. Observers still report unusual tail geometry, including structures that look deceptively sunward. Spectroscopy continues to highlight a composition that doesn't match every line in the standard comet cookbook. Infrared measurements suggest unusual balances of volatiles. Its path along the ecliptic, its size, its brightness, evolution, all of these keep it slightly off-center from what our intuition expects, even as official language presses it gently back toward the word normal. So now, instead of wondering what NASA will show, we're left to sit with what they have shown and with what's still quiet. The images themselves are striking. A small, bright core, wrapped in a delicate haze, caught from Mars's vantage point and from distant observatories across the solar system. But they are processed views, calibrated and stretched and smoothed for human eyes. The raw FITS files, the unpolished pixel grids that let independent teams test their own assumptions, are still on their own slower path through archives and data portals. They will come, in time, but not as instantly, not as theatrically, as the curated frames did. In the press event, most of what you might expect was there. Neat size estimates, with error bars tucked quietly into the narration. Models showing how jets could arise from sunlit patches of ice on a spinning body. Comparisons to Oumuamua and Borisov that place 3I Atlas in a growing but still tiny family of interstellar wanderers. You could hear talk of CO2, rich outgassing, of dust properties, of trajectories shaped by gravity alone. You could also hear, if you were listening for it, how quickly certain harder questions were stepped around. Why some features don't yet fit cleanly, how long raw products will remain internal, what role the long delay played in the wider global effort. None of this means anyone is lying. Big institutions move slowly. They worry about getting things wrong in public. They balance curiosity against caution, politics against pure science. But it does remind us that communication and transparency are not the same thing. A polished briefing, full of beautiful images, can still leave crucial pieces in shadow. True openness is quieter, less dramatic. It shows up in how quickly data appears in public archives, in how honestly uncertainties are acknowledged, in how willing an agency is to say, "We don't know," when the models don't quite fit. While NASA was preparing its story, others were already telling theirs. China's Tianwen-1 released its own early views from Mars orbit. Amateurs stacked hours of exposures into deep images that revealed delicate jets and faint structures. Small telescopes and backyard spectrographs added their threads to the tapestry. Hints of odd chemistry here, strange polarization there. The sky did not wait for anyone's permission. The object moved on, changing under sunlight, while the institutions on the ground decided how and when to talk about it. Now, with the official images finally laid out, you can let them be exactly what they are. One more set of eyes on a brief visitor that will soon be gone for good. You can enjoy the detail, the sense of being closer to something that came from far away. And, if you wish, you can also keep a small, steady awareness that what you've been shown is a curated slice of a much larger pool of data and interpretations. If 3I Atlas truly is nothing more than a dusty, CO2 rich interstellar comet with a few quirks, then, over time, independent analyses of the full dataset will let that picture settle in. Papers will be written, models refined, arguments cooled. If, instead, some of its behavior continues to push against the edges of our expectations, if the chemistry, the light, the motion keep resisting easy stories, then more complicated conversations will follow, slowly and quietly, long after the press lights have dimmed. Either way, you don't have to decide anything tonight. You can simply notice the gap between the promises of ultra-transparency and the slower, more careful reality, the difference between letting the universe speak and narrating it into something comfortable. Somewhere out there, 3I Atlas is already heading back into the dark, carrying its secrets with it. Down here, we are just beginning to decide how honestly we're willing to look at what it might have tried to tell us. Looking back now, with NASA's press conference behind us and the natural interstellar comet headline echoing through the news, that long pause before the images appeared feels different, not in the sense of clear physics or simple openness, but in the quiet way big institutions manage risk. The promises of ultra-transparency live in one world. The slower, more cautious behavior lives in another. To feel why that gap still matters, even after the official verdict, it helps to rest your attention for a moment on the puzzle of 3I Atlas itself. Astrophysicist Avi Loeb has sketched out 12 separate anomalies linked to this one visitor. They are not tiny quirks that vanish if you nudge a model. They are places where 3I Atlas leans hard against what we expect from natural comets, and the odds of all 12 showing up together drift into numbers so small they feel almost abstract. Any one anomaly might be survivable for the standard story. Together, they bend that story into a different shape. The first lives in the path it takes, a retrograde orbit aligned with the solar system's thin planetary plane, the ecliptic to within about 5 degrees. For a truly random interstellar arrival, directions should be scattered across the sky. Hitting that narrow band is estimated at only a few tenths of a percent. The second is the sunward jet, an anti-tail seen in multiple observing windows. Sunlight should push dust away, so tails stream outward from the Sunday. To see material apparently extending sunward, something has to overcome that outward push and send dust back toward the light. Simple ice turning to vapor does not do that. The third ties mass and speed together. Estimates suggest that 3I Atlas is vastly more massive than Oumuamua and Borisov, yet moves faster than both. In the early statistics of interstellar wanderers, big and fast is an uncommon pairing. Larger objects are more easily slowed or captured by gravity along the way. The fourth concerns timing and geometry. 3I Atlas threaded a path that brought it close to Mars, Venus, and Jupiter, while arranging its closest approach to the Sun, so that from Earth it lay lost in the glare. For something arriving from between the stars to pass that near several planets and yet be unobservable from Earth at perihelion is a choreography with long odds if everything is left to chance. The fifth moves from orbits to chemistry. In gas seen around 3I Atlas, some observers report nickel far outweighing iron. Normally, those elements are forged and mixed together in fairly fixed ratios. Here, nickel seems to dominate without matching iron, odd for a natural blend. strangely reminiscent of nickel-rich alloys we design for strength and heat resistance. Anomaly 6 is the water problem. In some analyses, only a small fraction of the measured gas mass appears to be water. In the conventional picture, comets are dirty snowballs. Water ice is their main volatile, and when you warm them, water vapor gushes out first and in abundance. A tiny water fraction suggests a largely dry body with only a thin frosting of ice. The seventh involves polarization, the way dust changes light's orientation. 3I Atlas shows an unusually strong negative polarization signal, not seen in other comets, even the already odd Borisov. The pattern does not match existing measurements for comet dust or any well-studied natural cometary material. The eighth is easier to shrug off, but it lingers. The incoming direction of 3I Atlas falls within about 9 degrees of the patch of sky associated with the famous WOW radio signal of 1977. 9 degrees is wide enough that coincidence is plausible. On its own, this would be a curiosity, nothing more. But on a growing list, even gentle alignments feel like another strand in the weave. Anomaly 9 unfolds near perihelion. Reports suggest that 3I Atlas brightened faster than any comet on record, and instead of reddening as it warmed, its overall color drifted bluer than the Sunday. Usually, as comets heat, dust and thermal glow pull their light toward the red. Blue-leaning emission hints at extremely fine dust, or some process emitting strongly at shorter wavelengths. And the speed of brightening outran simple sublimation curves. The 10th returns to jets and energy. The combined sunward and anti-sunward plumes imply that a certain mass must be lifted from the surface. For simple sublimation to manage that, the object has to absorb enough sunlight over enough effective area to power all that gas and dust. When you work through the thermodynamics, the books do not quite balance. Anomaly 11 focuses on motion. Near perihelion, 3I Atlas showed non-gravitational acceleration, small, but real deviations from the path gravity alone would dictate. To get that sort of push from outgassing, calculations say a large fraction of the object's mass would need to evaporate. When ordinary comets lose that much material near the sun, they fragment. Early imaging, though, suggests that 3I Atlas stayed in one piece. The 12th is quieter but deeply suggestive. Observers see narrow, collimated jets that keep their orientation over enormous distances, pointing in several directions relative to the sun, even though the nucleus appears to rotate. On ordinary comets, jets sweep across space like turning searchlights. For 3I Atlas, they seem to hold their aim, which would require either an extraordinarily slow spin or some mechanism that actively adjusts jet directions. Step back, and you are holding 12 separate oddities. Each carries a small probability, some a few percent, some tenths or hundredths of a percent. If you treat them as independent, their combined likelihood plunges. Multiply enough tiny chances together, and you sink into territory that, while not literally zero, strains belief. If you insist this is all just random luck in a natural comet that happens, curiously, to come from another star. This is where conventional explanations begin to feel stretched, even as official statements quietly repeat interstellar comet until it sounds like closure. You can, with effort, build a natural story for any one of these anomalies. A rare alignment here, an unusual birth environment there, long-term irradiation to strip water away. Each patch may work on its own, but to cover all 12 at once, you have to stack special cases on special cases until the tower looks more like a card house than a simple answer. At that point, something like Occam's razor, the preference for simpler explanations starts to turn in an unexpected direction. One alternative is that these anomalies are not independent at all. A single underlying cause, or a small family of causes, could produce several of them together. When you quietly ask what sort of common cause could fine-tune a trajectory, twist chemistry, steady jets, preserve structure under non-gravitational acceleration, and arrange planetary flybys that happen to be hidden from Earth at closest approach, your thoughts drift outside the usual formed naturally and left alone category. What if the alignment with the ecliptic is not just a fluke, but a kind of targeting? What if the low water content is not depletion, but design? What if jets that keep their aim despite rotation mark some kind of active control? These questions sound like they belong to science fiction, and perhaps they do. There may be exotic natural pathways we have not yet imagined, strange birthplaces around unusual stars that sculpt a body into exactly this shape of oddity. But intellectual honesty asks, just for a moment, that we widen the frame. A constructed object, a deliberate trajectory, an artificial origin. These ideas should not be thrown away simply because NASA's first label is comet, or because they feel uncomfortable to hold. They are not automatically less plausible than a dozen unrelated natural surprises all stacking up in one small, distant visitor. The point is not to declare that 3I Atlas is artificial. The point is gentler. Artificial origin deserves to sit among the hypotheses we test, not outside the door. If we rule it out in advance, simply because it unsettles us, we quietly guarantee that we will never recognize an interstellar artifact, even if one passes right through our backyard. The 12 anomalies are not proof. They are soft-spoken clues that, taken together, suggest this object does not sit easily within our current expectations. They merit careful investigation without the ending written beforehand. The high-resolution images NASA has now released may soften some of them, revealing surface structures that make the jets behave more like we expect, or subtle fractures that explain the mass budget, or hints of fragmentation that earlier data missed. Or they may add one more oddity to the stack, and somewhere in that growing, wobbling pile, the weight of the strange will finally become too much to quietly smooth away. While people argued over probabilities and labels in conference rooms, something quieter was unfolding under much smaller domes. While major observatories refined their models, and NASA moved slowly at first, then finally toward releasing its high-resolution images of 3I Atlas, observers with modest telescopes were recording shapes that, by our usual rules, simply shouldn't have been there. They started calling it the ghost shell. At first, it was barely more than a suggestion, an almost invisible ring wrapped around 3I Atlas, like a smoke circle someone had blown into space and then forgotten. It wasn't a fuzzy blob or a streak, it was a circle. On November 9th, that ring measured about 1.2 arc-minutes across. 4 nights later, on the 13th, it had grown to about 1.4 arc-minutes, a roughly 20% increase in just 4 days. Expansion, by itself, isn't strange. Material leaves a comet, moves outward, thins. That's what comet and tails do. What made this different was how the ring behaved as it grew. It stayed circular, uncannily circular. A real nucleus is not a smooth sphere with a single clean vent. It's lumpy, irregular, scarred with pits and cliffs, rotating at its own awkward pace. Jets burst from some regions more than others. As the body spins, those jets sweep around, creating spirals, twisted fans, uneven plumes. The dust and gas they shed tend to be messy, thicker in some directions, thinner in others. Torn by rotation and changing activity, symmetry breaks quickly. What you do not expect, what no standard model predicts, is a thin, nearly perfect circle expanding away from the nucleus while keeping its shape as if drawn with a compass and gently inflated. Yet that is what multiple independent observers reported: a pale, circular shell swelling outward at a steady pace. It behaved less like a random spray and more like a bubble released by a single, sharply defined event. But 3I Atlas itself is not a point. It is kilometers across, with multiple active regions and complex terrain, already known to throw jets in different directions. The geometry of that reality and the geometry of the ghost shell sit uneasily together. Then came the stranger part. The shell was not alone. With deeper exposures and more careful processing, several observers began to see not one ring, but several 5 distinct concentric shells separated from each other, spread across a region roughly 150,000 kilometers in size. Not solid walls, not a smooth bubble, but clear ring-like edges, bright, thin circles with darker gaps between them. For scale, 150,000 kilometers is on the order of 40% of the Earth-Moon distance. Imagine a stack of ghostly hoops nested around an interstellar visitor, stretching across a volume larger than many planetary systems, and yet showing spacing, layering, regularity. Normal coma physics doesn't do this. When a comet releases gas and dust, the result is a hazy glow that fades gradually with distance. Density drops off smoothly. Any structure softens over time. You can see jets, arcs, even broad shells from repeated outbursts, but cleanly separated rings with sharp edges and measurable gaps are not part of the usual picture. What makes it more striking is who saw it first. These images weren't taken by the largest mirrors on the planet or by NASA's own spacecraft. They came from backyards and small observatories, consumer-grade cooled cameras, modest telescopes, tracking mounts bought by people who save and tinker and stay up late for this kind of thing. Professional surveys are often tuned for other goals. Their pipelines hunt for moving points, measure light curves, catalog galaxies. Automated routines are trained to reject anything that looks like a reflection, a ghost, a processing artifact. Unusual geometry can be discarded without a human ever really looking at it. Amateurs, by contrast, stare at the same patch of sky for hours. They stretch their images in different ways, compare night to night, learn every quirk of their sensors. They know the usual ghosts, the internal reflections, the filter edges, the dust specks, and how to calibrate them away. So when observers using different telescopes, cameras, optics, and software all began to report the same delicate circles around 3I Atlas, the easy explanations, just an artifact, just a glitch, started to fade. Processing mistakes do not reproduce themselves in the same pattern across independent setups. Instrument ghosts do not line up identically for different instruments. The simplest remaining conclusion was the uncomfortable one. The shells are real. They are out there, and they need explaining. Naturally, people began to ask, what could cause such structures? The most conservative idea imagined a series of distinct outbursts. If 3I Atlas had several major eruptions separated in time, each could cast off a roughly spherical wave of material expanding outward. Over time, those pulses might appear as nested shells. On paper, you can make that work, but only with careful assumptions. Each burst has to be brief and nearly isotropic. releasing material almost equally in all directions. Velocities have to differ enough for the shells to stay separated. That picture doesn't match what we usually see from jets. They are directional, shaped by local topography and sunlight. To smear them into a smooth sphere, the nucleus would need to rotate quickly during each burst, sweeping active regions across the sky in a short window. Observations so far suggest 3I Atlas doesn't spin that fast, and some jets appear to keep their orientation instead of sweeping broadly. That makes the perfect spherical burst scenario hard to reconcile with the rest of what we know. Another idea looked outward to the environment. Perhaps material from 3I Atlas is being shaped by the solar wind and the sun's magnetic field, organized into ring-like forms by magnetohydrodynamic effects. It's true that the solar wind has structure. It carries embedded magnetic fields, follows the Parker spiral, pulses with solar activity. Those fields can affect charged particles, bending paths, and sometimes sculpting subtle forms. But the wind is thin. It nudges. It rarely carves with precision. To produce thin, discrete rings with sharp boundaries, the forces would have to be both strong and delicately balanced, overcoming the natural tendency of particles to spread and mix, while dealing with changing field directions and fluctuating pressure. The rings around 3I Atlas look too clean, too regular for such a fragile sculptor. A third line of thought stepped closer to the edge of what we understand. Perhaps these aren't separate shells from separate outbursts at all, but patterns born of waves, standing waves, in the coma. Imagine material flowing outward and encountering some invisible structure or field configuration that sets up oscillations. High-density regions become bright rings. Low-density regions fall into the gaps. From our distance, those crests and troughs could look like concentric hoops, frozen patterns in a trembling medium. Standing waves usually need boundaries, places where waves reflect and interfere, building up stable nodes and antinodes. Around a comet, there are no obvious walls, unless the object itself supplies a kind of boundary, a strong local magnetic field, a magnetosphere interacting with ionized gas. But comets, as we currently understand them, don't host that sort of magnetosphere. They lack the internal dynamos that power planetary magnetic fields. Giving 3I Atlas that ability would require conductive structures and current systems far outside standard comet models. Through all of this, the amateurs kept watching. These were not casual snapshots. Many of these observers have spent years, even decades, imaging faint comets and galaxies. They stacked exposures, subtracted noise, checked their calibrations. When something odd appeared, they did not shout first. They double-checked, re-imaged, and asked others to confirm. In one careful sequence, an observer stitched together images from multiple nights, frame by frame. The ghost shell swelled outward from the nucleus, growing larger but staying round from the expansion rate. They estimated a speed of about 500 meters per second, perfectly reasonable for dust and gas drifting gently away. What remained unreasonable was the discipline of the shape. Across tens of thousands of kilometers, with the nucleus rotating, jets flickering, and the solar wind whispering through, the ring stayed round. No obvious bulges, no major distortions, just a thin, expanding circle traced on the night. Another observer noticed that the rings were not perfectly uniform in brightness. Around the circle, faint variations appeared, patches slightly brighter or dimmer, but they did not look random. They seemed to repeat at certain angles, hinting at preferred directions or alignments. Perhaps with the solar wind, perhaps with the ecliptic, perhaps with something we haven't recognized yet. The data was too limited to be sure, but the suggestion of order was there. The detached shells also raise a simple practical question. Mass. To form several visible rings, each thousands of kilometers across, and bright enough for small telescopes to record, a significant amount of material must be involved. That dust and gas has to come from somewhere. Is 3I Atlas shedding its outer layers in great spurts, eroding like an onion under the sun? If so, its shape and mass should be changing in ways we might eventually notice. Or is material somehow cycling, released, reorganized, perhaps interacting with fields and flows in ways we don't yet understand? Some professional astronomers did notice the rings. They reached out to the amateurs with the clearest images, requesting raw data, calibration frames, exact setups. A few collaborations sparked. Scientists and hobbyists trading files, checking each other's work. But in NASA's main briefing, and in most public summaries, the shells were barely mentioned, if at all. The focus stayed on the nucleus, the interstellar origin, the official classification, a comet from another star. Features that didn't fit easily into that neat frame drifted quietly to the margins. That isn't entirely surprising. In astronomy, caution around unvetted claims is healthy. Artifacts exist. Processing can mislead. Independent confirmation matters. But for a transient visitor, like 3I Atlas, time moves faster than our paperwork. While data is being checked and drafts are reviewed, the object is already on its way out. Structures that were crisp in November may be soft by December, gone by the time a formal paper sees the light. In that sense, the ghost shell mystery isn't only about one comet-like object. It touches a deeper question. How do we study things that pass quickly through our field of view, changing as they go, giving us only a single chance to really see them? 3I Atlas is not holding still while we argue. Its coma thickens and thins. Jets turn on and fade. The shells, whatever they are expanding and growing fainter, slowly sliding from barely visible toward gone in the span of a season. The high-rise images that NASA has now shared are extraordinary in their own way, resolving the core from a vantage point no Earth-based telescope could match. But they are tuned for certain priorities, resolving the nucleus, capturing the inner coma. If the shells lie at very low brightness levels, or mostly outside the chosen field of view, they may be invisible in those first public frames, washed out by exposure choices, lost in limited dynamic range. What the amateurs have already shown, beyond argument, is that 3I Atlas is more structured than a simple, dirty snowball. The closer and more patiently people look, the more layers appear. And when some of those layers are almost perfect circles, concentric shells, regular spacing hallmarks of geometry, gentle, unsettling questions naturally rise. Are we watching physical processes we don't yet understand? Interstellar crusts behaving strangely when warmed, fields and flows setting up patterns we haven't modeled? Or, very quietly, are we looking at something that holds its shapes because it was meant to hold them? A system that maintains form the way a mechanism follows instructions? For now, the shells belong to no official story. They sit between worlds, confirmed enough to be real, uncertain enough to be ignored. They're still expanding out there in the dark, written as faint, precise lines across a huge volume of space, waiting for better images, deeper analysis, and a place in whatever honest story we eventually tell about what 3I Atlas truly is. While those ghostly rings were swelling outward in slow motion, another kind of investigation was quietly unfolding, not with big mirrors or spacecraft, but with a small refractor, a diffraction grating, and someone patient enough to sit under the night and let light turn into numbers. A civilian observer, working with an 80mm refractor, a star analyzer 100 grating, and a cooled monochrome camera, pointed their modest setup at 3I Atlas and did something very simple and very powerful. They broke its light apart. Instead of just a picture, a bright green fuzz with jets and shells, they pulled out a spectrum, a thin rainbow stretched across a sensor, full of clues about what that glow is made of. They wrote custom Python code to extract that rainbow cleanly. They subtracted nearby starlight, corrected for the response of their equipment, and calibrated the wavelengths against known standards. The range they captured ran from about 628 to 880 nanometers, the deep red edge of visible light sliding into the near-infrared, a window where several familiar cometary gases often leave their marks. When they were done, they were left with 30 clear spectral peaks, 30 places where the light rose above the background continuum, each one a potential fingerprint of some molecule or atom around this interstellar visitor. In that particular spectrum, not one of those peaks belonged to a commonly seen gas. That is the heart of the puzzle. Remember what 3I Atlas looks like in ordinary images. It carries a bright green coma. It throws off strong jets seen by multiple observers. It clearly releases material that forms structures tens of thousands of kilometers across. Everything about its appearance says active comet, boiling and venting under sunlight. On a normal comet, a spectrum from such a scene should be crowded with gas signatures. You would expect to see CN bands, C2, swan bands, CO mice lines, features from water and other common volatiles, all the familiar shouts of molecules excited by the Sunday. Instead, in this civilian spectrum, the light was almost completely quiet in that language. No CN, no C2, no CO mice, no water bands in the covered range, nothing. The green color makes this even stranger. In every well-studied comet with a green coma, that hue comes from diatomic carbon molecules, C2, fluorescing under solar ultraviolet light. The swan bands they produce in the green are so reliable that green comet has become shorthand for C2 is present. But here, in this slice of data, 3I Atlas glows green without any detectable C2 lines in the observer's window. Naturally, the first suspicion fell on the measurement itself. Maybe the spectral resolution was too low, and the lines were smeared into the continuum. But the spectrum wasn't a noisy blur. It was clean and sharp. 30 distinct peaks stood out. If strong C2 emission had been present at levels bright enough to paint a visible green coma, it should have risen above the noise easily in any range that covered those lines. Maybe the problem was the wavelength coverage. The brightest C2 bands sit closer to 516 nanometers in the green, while this observation started at 628. Perhaps the main swan bands were simply out of frame. That's possible, and other, larger instruments have since reported gas in different bands. But even so, other species have features in the captured range. CN leaves traces there. Water and several other cometary molecules usually lend at least a few bright threads. In this data set, they did not. Maybe the comet was in a lull when the spectrum was taken. Jets briefly quiet, gas emission low, but images from the same night show a bright coma and active structures. Material was clearly flowing out. It is hard to reconcile a visibly vigorous comet with a spectrum that shows only dust, because that is what the spectrum did show, dust and nothing else. The continuum had a red slope, consistent with grains darkened and aged by radiation. The peaks that were present could be modeled as features of thermal emission from solid particles warmed by the sunday. Temperature estimates matched what you would expect for dust at that distance from our star. In that sense, the result lined up with hints from larger observatories. In this part of the spectrum, 3I Atlas looks like a red, dusty object with very little detectable gas. That picture fits an inert asteroid or a heavily processed remnant. It does not sit comfortably beside the site of a bright green comet with huge jets and organized shells. So we arrive at a fork. Either the green is not coming from the usual gas emissions we rely on, bending a rule that has held for every comet studied so far, or there is gas present but made of species or behaving under conditions that push its signals outside the window and resolution used here. In either case, the standard textbook link between green coma and C2 emission is not working cleanly in this particular observation. There is another, quieter implication. A smooth, featureless red continuum is exactly what you would expect from sunlight, reflected off a solid surface covered in fine dust. Whether that surface is an ancient natural rock or a shield of engineered material, if the dust is thick enough or the outer layers are uniform, the spectrum stops telling you much about what lies inside. It simply says, warm grains, lit by the sunday. That means spectroscopy alone, in this narrow band, cannot tell us whether we are seeing an ordinary dust-coated body or something more deliberate, wrapped in regolith. Both would look similar at these wavelengths. The data does not shout artificial, but it also cannot be used to wave artificiality away. Meanwhile, the jets themselves continue to refuse the role of simple plumes from boiling ice. On November 15th, observers reported 3I Atlas with a green coma, but no strong jets, a relatively calm face. On the 16th, just one day later, jets had come roaring back broad, symmetric plumes pointing both toward and away from the sunday. The change was not a gentle modulation. It felt more like a switch being flipped. Natural comet jets track sunlight. As a nucleus rotates, active regions move into daylight and then back into darkness, and jets wax and wane with that spin. They can vary on timescales of hours, but large active areas do not usually shut off almost completely for a full day and then reappear at full strength, as if on a schedule unrelated to the rotation. To do that with pure solar heating, you would need an exceedingly slow spin rotation periods, measured in days, and very particular arrangements of active patches, or you need something else controlling when the jets turn on and off. Put that beside the dust-only spectrum, and a particular outline comes into view. Visible activity that looks comet-like, driven by a mechanism that may not be normal sublimation of water and simple volatiles, at least in this wavelength range. What could that be? One possibility stays as close as it can to standard physics. Dust jets without significant accompanying gas can, in principle, arise if very fine particles are lifted by electrostatic forces or by mechanical disruptions, fractures, landslides, internal stresses that fling material outward. But such jets tend to be less sharply collimated and weaker than what we see around 3I Atlas, and even then, a little gas from surface frost would usually be expected. Its apparent absence remains a problem. Another possibility leans into plasma. As 3I Atlas moves through the solar wind, it may build up electric charge. If that charge is released in bursts, the resulting discharges could accelerate dust and ions into narrow plumes. Plasma glows can be green under certain conditions. In that scenario, the coma's color might come from ionized material rather than from familiar molecules like C2. Yet to create recurrent plasma jets, you need an environment that can generate and sustain significant electrical currents, a level of internal organization we do not normally assign to comets. It is not impossible in principle, but it stretches the usual story. It is also true that this civilian spectrum sampled only one slice of a much larger picture. If 3I Atlas is rich in unusual molecules that radiate mostly in the ultraviolet, or if its key signatures lie deep in the infrared, this observation would miss them. Larger observatories, some of which have already begun to share broader, higher resolution spectra, will gradually fill in more of that chemical portrait. But those instruments live on telescopes with busy schedules, and 3I Atlas is already fading and moving on. Our best window for clean, repeated spectroscopy will never come back exactly as it is now. That is part of why this small aperture spectrum still matters, even after NASA's high-rise images and official interstellar comet framing. It exists because someone decided not to wait for perfect conditions or formal campaigns. They gathered light, turned it into data, and then did something precious. They shared everything. The raw files, the processing scripts, the calibration steps, all of it was posted openly, inviting others to test and critique their work. In its own quiet way, that level of openness stands in contrast to the long hold that preceded the release of the sharpest Mars-based images. While agencies crafted their narrative and timing, an individual with modest tools simply showed the sky as it was on a particular night, with all the awkwardness of an impossible result intact. The spectrum itself cannot tell us, on its own, whether 3I Atlas is a primordial shard from a forgotten system or something more deliberate and built. It cannot decide between extremely old natural dust and carefully shielded structure. What it can say clearly is that in this window, this object does not behave like the comets we thought we understood. If it were a classic water-rich comet, bands from water and other volatiles should be there. If it were a straightforward carbon-rich comet, C2 lines should be blazing somewhere in the appropriate range. If it were a completely inert rock, the absence of gas would make sense. But then the jets, the shells, and the vivid coma would need a new script. Some have suggested that 3I Atlas is exactly what early whispers proposed, a primordial relic, dust and rock formed far from any star, processed for eons by cosmic rays until only a hardened crust remains. That might explain the red continuum and the lack of easy volatiles in certain bands, but it leaves the intermittent jets, the green glow, the ghost shells, and the steady, collimated plumes awkwardly hanging. Others have quietly allowed themselves to imagine an interstellar probe designed to endure, something wrapped in dust and radiation shielding, drifting for ages between suns. From the outside, after so long, it would look like a lumpy rock. Its spectrum would be dust-dominated and bland. Only when it neared a target star might hidden systems awaken, venting material in ways that do not follow the gentle logic of sublimating ice. Both pictures are speculative. Both sit near the edge of what we can responsibly claim, but the spectral result does not let us retreat fully to comfort. It tells us that, in this red and near-infrared window, 3I Atlas is dust and silence where there should be gas and song. High-rise does not add new spectra. It adds sharper images. Those images, already released in part, will be pored over for surface colors, textures, and patterns. If they end up matching the dried-out natural body, some of these puzzles may soften. If they reveal structures that look oddly organized, or if they show nothing that can easily power the observed jets, the mystery will deepen. instead. Either way, this impossible spectrum remains a fixed point, a bright green coma with no detected classic gas lines in this range, large, symmetric jets with no obvious volatile engine in the observed band, 30 peaks telling us what is their dust, and an empty space where everything we expected to see has, for now, refused to appear. From the strange quiet in the spectrum, it feels natural to drift back to where 3I Atlas is loudest, its jets. The more patiently observers have tried to understand those plumes, the more they seem to lean against some of the simplest rules we tell ourselves about how matter behaves under sunlight. Not tiny quirks, not little mismatches you can blame on noisy data, but tensions with very basic ideas about energy, momentum, and how gas expands into vacuum. It begins with the energy. When ice turns straight into gas, it has to pay a fixed price in heat. That cost is the latent heat of sublimation, and out there, the only real source of payment is the sunday. At any given distance, you can work out how much solar power falls on a square meter of surface, adjust for how dark or bright the material is, and how much heat leaks away, and from that, estimate how much ice can realistically turn to gas each second. These aren't exotic calculations. They're the kind of energy in, energy out problems that live near the start of a thermodynamics textbook. Near perihelion, 3I Atlas was bathed in strong sunlight, more than enough to drive serious sublimation if water or other volatiles were lying exposed. But when you take the jets we actually see in images and treat them as real flows of mass, the account doesn't quite balance. The amount of material implied by those narrow plumes calls for sublimation rates that, in turn, demand more sunlit surface area than the nucleus seems to possess. Even if you're generous and let every photon do nothing but tear molecules free, no heat lost sideways, none radiated away, the effective area needed to feed the jets starts to outrun reasonable size estimates for the body itself. On top of that, the jets are not soft fans, fading gently into the coma. They are collimated, tight, beam-like structures that hold their narrowness over astonishing distances. In ordinary comets, some focus is expected. Gas venting through a crack or pit can emerge as a stream, and nearby cliffs can act like a crude nozzle. But those effects live on scales of meters to tens of meters, and the resulting jets typically broaden with distance, mixing into a more diffuse glow. Around 3I Atlas, the main plumes stay sharp across thousands of kilometers. They look less like puffs of boiling ice and more like sustained beams. Then comes direction. Observations of its changing brightness, along with careful tracking, suggest that 3I Atlas rotates. Different faces turn toward and away from us. The light curve breathes in a repeating pattern. On a typical comet, jets are anchored to specific, active patches. As the nucleus spins, those patches move, and the jets trace arcs, spirals, and fans across space. Here, some of the key features seem to hold their aim. The sunward structure that behaves like an anti-tail, and the long, narrow tail streaming away from the sun, don't appear to sweep widely with rotation. They keep roughly fixed orientations in space. For a spinning body, there are only two broad ways to arrange that. One is to line up the rotation axis almost perfectly with the jets, so that the spin doesn't change their direction. But to keep both a sunward feature and an anti-solar feature aligned, while also accommodating other plumes at different angles, asks for a geometry that starts to look less like chance and more like fine-tuning. The other option is subtler. Something about the way the jets are produced compensates for the spin. As the nucleus turns, the source regions would have to adjust in such a way that the overall direction of the outflow stays nearly constant. Natural outgassing doesn't have that kind of steering. It happens where the heat is, when the heat arrives. Keeping a jet locked onto a particular direction in space begins to sound like some kind of vector control nozzles that can point, or active areas that switch on and off in a coordinated pattern. Layered over this is the rhythm of the activity itself. Observers have watched jets blaze strongly on one night, almost vanish the next, and then return a day later at similar strength. That on-off cycling has appeared more than once. If the main engine is just ice responding to sunlight and spin, you'd expect something more gradual, a rising and falling with distance from the sun, and a modulation over hours as different regions rotate into daylight. You can get flickering, but a whole system that seems to quiet down for roughly a day and then come back with the same intensity asks for a particular arrangement. Large active zones confined to one side, long stretches spent in shadow and then in light, and a rotation period tuned just so. Most comets don't behave that neatly. Their activity comes from multiple spots scattered across the surface, overlapping to create a more continuous, noisy pattern. The sunward jets add another twist. In the simple picture, dust and gas, pushed by radiation pressure, drift away from the sunday. Photons carry tiny bits of momentum. When they hit grains, they give them a nudge outward. That's why comet tails, in children's drawings, and in real images, generally stream away from the star. To move material genuinely sunward, you have to push against that. Some other force must be strong and focused enough to overcome both radiation pressure and whatever initial shove the material got as it left the surface. In some cases, anti-tails are illusions, a sheet of dust lying in the orbital plane that, from our perspective, seems to point back toward the sun, while the particles are in fact moving away. For 3I Atlas, careful geometry from different vantage points suggests that at least part of the sunward structure is not just a projection trick. There appears to be real motion of material toward the sun, or at least arranged sunward in a way that simple models struggle to mimic. Electric fields could, in principle, pull charged particles inward. If the coma and the surrounding plasma environment arrange themselves just right, ions might flow in unexpected directions. But to move a substantial bulk of dust that way, fields would have to be impressively strong and organized, calling for charge separation and electrical structures we don't normally expect to arise spontaneously around small, fractured bodies adrift between the stars. Gravity is another tempting handle. Perhaps, one might imagine, material lofted from the far side of the nucleus swings around under its weak gravity and emerges on the sunward side, tracing something like a jet. But 3I Atlas is only a few kilometers across. Its escape velocity is measured in meters per second. Ordinary gas speeds from sublimation are in the hundreds of meters per second. Most particles won't stick around long enough to orbit gracefully. They will simply leave. The mass loss estimates make the whole picture wobblier still. By looking at the small deviations in its path, those non-gravitational accelerations, you can infer how much net thrust must be acting. If all of that thrust comes from outgassing, then a certain mass of material has to be expelled to provide it. For 3I Atlas, the numbers point towards something like 13% of its total mass being lost near perihelion. 13% is not a gentle trimming. For a fragile, loosely bound body, losing that much in a short span is often fatal. We've watched other comets fly too close to the sun and shatter, surrounded by clouds of fragments that tell the story of their unraveling. So far, 3I Atlas has not obviously done that. In the images now released from Mars orbit and from Earth-based facilities, it appears as a coherent nucleus wrapped in a coma, not as a string of broken pieces. At the same time, the surrounding cloud does not look bloated enough to easily hide the kind of enormous mass ejection the simple calculations suggest. It's always possible that some part of the maths is off, or that the thrust is more efficient than our first estimates assume. A highly directional jet can provide more push per unit mass than a gentle, even flow, just as a rocket engine is more effective than steam, drifting from all sides at once. But even when you give that idea as much room as you can, a gap remains. Either a lot of missing material is spread in ways we have not yet measured, or some slice of the acceleration is coming from something other than straightforward gas loss. Any one of these tensions, energy, direction, timing, mass, might, on its own, be patched with a creative natural story. Perhaps 3I Atlas is unusually dry, with small pockets of volatile material that flare up in sudden bursts. Perhaps its surface is carved into deep, narrow vents that mimic nozzles and valves, turning chaotic boiling into tidy beams. Perhaps its long time in interstellar space has left it cracked and layered in ways that fail dramatically when warmed. But to cover everything at once, using only those tools, means stacking rare conditions on top of rare conditions. That is why thoughts, even in cautious minds, keep circling back to the idea of control. Control doesn't have to mean intention or intelligence in a softer sense. It just means feedback, any mechanism that regulates what comes out based on what is happening, rather than letting things unfold purely from where heat happens to land. In our own machines, whenever we want thrust that points and pauses and resumes on cue, we build precisely this kind of system: nozzles, actuators, sensors, loops that constantly adjust. Could nature, somewhere between the stars, build something that behaves similarly without anyone designing it? Maybe. In strange environments, geology can imitate machinery. Vents can open and seal. Cracks can guide flows. Layered materials can fail in patterns that look uncannily organized. We don't know yet how often that happens, or how far it can go. For now, the jets of 3I Atlas continue to follow whatever hidden rules shape them. As the comet moves away from the sun, some reports suggest its activity is easing. Others still find structure flickering in deep images. Official analyses, including NASA's, continue to treat it as a natural interstellar comet, even as they acknowledge that its behavior is unusual and still under study. Each new observation adds another small piece to the picture. But instead of settling smoothly into a familiar pattern, those pieces keep tugging at the edges of what we thought comets could do. The physics at work is real and consistent. It's our picture of that physics that feels unsteady. Somewhere inside the behavior of these jets, there is a lesson about energy, momentum, and the possible lives of objects that wander between stars, a lesson we are only just beginning to hear. From the strange behavior of 3I Atlas's jets, it's a small, gentle shift to look up at something far more familiar. The tiny, sparkling knot of light we call the Pleiades. On clear nights, you can see them with the naked eye, a little cluster that to most of us has always been 7 stars, the 7 sisters. For a long time, even with telescopes, they seemed to be just that, plus a few hundred fainter siblings gathered tightly together, a pretty, compact family hanging in the dark. But that picture, it turns out, was as incomplete as calling 3I Atlas just a comet. New work has shown that the Pleiades are not a small, cozy cluster at all, but the bright, visible heart of a structure so large it's hard to hold in your mind. Instead of a few hundred stars packed into a pocket of space, there are more than 3,000 related stars spread across roughly 2,000 light-years, about 20 times larger than anyone suspected. We have been looking at this object for as long as humans have looked up. The Pleiades appear in ancient stories and sky maps from almost every culture that had clear nights and patient eyes. They anchor creation myths, calendars, navigation traditions. The Greeks named them the Seven Sisters. Their pattern is stamped into the Subaru logo in Japan. These are not obscure, distant galaxies that require billion-dollar observatories. They are right there in the open, visible from a backyard. And still, for centuries, we were wrong about what they truly are. The revelation did not come from a single new telescope staring only at the Pleiades. It came from quietly combining several very different kinds of data pieces that were originally gathered for other purposes. NASA's TESS spacecraft was built to hunt exoplanets by watching for tiny dips in starlight. But while it watched, it also recorded how those stars' brightness flickered over time. Those subtle variations can reveal rotation rates. Young stars spin fast, and as they age, they gradually slow down. Spin becomes a kind of clock. By measuring how quickly a star turns, you can estimate its age. Researchers noticed that thousands of stars scattered across a wide region near the Pleiades all shared nearly the same clock reading. They were the same age, to a surprising precision. That is not something you expect from random stars picked out of the galaxy. It is what you see when a group of stars were born together. The European Space Agency's Gaia mission added another crucial piece. Gaia maps positions and motions of more than 1 billion stars with exquisite accuracy. It tells us not just where stars are, but how they are moving through the galaxy right now. If you know both position and motion, you can roll time backward, tracing each star's path into the past to see whether many of them once occupied the same region of space. When astronomers did this for the stars around the Pleiades, their paths converged about 100 million years ago, a time when all these scattered points were gathered into a single, dense, star-forming cloud. A true family, long since stretched out by galactic tides. A third line of evidence came from chemical surveys like the Sloan Digital Sky Survey. Stars, born from the same giant molecular cloud, share a chemical accent, similar proportions of elements heavier than helium, shaped by the particular history of supernovae and stellar winds that enriched their birth material. By measuring those abundances with spectroscopy, you can tag stars that were likely born together, even if they now lie far apart. Across the full 2,000 light-year span of this extended Pleiades complex, the stars share that chemical fingerprint. Same age, same motion history, same chemistry. Rotation, kinematics, and composition all point to the same conclusion. This is not just a tight clump of 7 bright stars, but a sprawling family whose members have wandered far, yet still carry the marks of their shared origin. Most star clusters don't stay tightly bound forever. Over hundreds of millions of years, the gentle pull of the galaxy and repeated tugs from other masses stretch them out, mixing their members into the general stellar background. What look like isolated field stars near the Sun may in fact be siblings, separated by hundreds of light years, still carrying subtle reminders of a common birth cloud. The techniques used on the Pleiades' rotation-based ages, Gaia's motion tracing, chemical tagging, give astronomers a way to uncover those hidden relationships. And once you see one famous cluster swell from a tiny knot into a 2,000 light-year wide complex, a quiet realization follows. We may have been underestimating the scale and structure of many stellar families. If the Pleiades are 20 times larger than we thought, how many other clusters are really just bright cores of much wider associations? How much of the stellar neighborhood around the Sun is organized into these extended families rather than being a random sprinkle? This loops gently back to 3I Atlas and the question that hovers behind all its anomalies. Where did it come from? Not just another star, but what kind of stellar environment? A quiet, single star like the Sun, where planetary systems can evolve in relative peace. A dense cluster, where stars pass close to one another, stirring up comets, asteroids, and planets in long, slow gravitational dances. A young association full of massive, short-lived stars exploding as supernovae, flooding nearby systems with radiation and heavy elements. The Pleiades, for example, are young, about 100 to 150 million years old. Many of their brightest members are massive blue stars racing through their fuel. In a few 100 million years, those giants will die in spectacular supernova explosions, pumping fresh elements into space and further disturbing whatever remains of the cluster's structure. 3I Atlas, by contrast, appears to be much older. Its surface bears the marks of long exposure to cosmic rays and interstellar radiation. Estimates put its age in the billions of years. It has been traveling between stars for longer than the Pleiades have even existed. When 3I Atlas began its journey, the Sun itself was younger, and many of the familiar patterns in our sky had not yet formed. In that sense, this object is a messenger from an earlier chapter of the galaxy's story, a piece of ancient material carrying information about environments that no longer exist in their original form. The extended Pleiades complex also invites a wider question. Is this kind of vast, dispersed family typical? Are most stars born in clusters that later slowly dissolve? Is our Sun part of an extended family that we have not fully mapped yet? Astronomers are beginning to search for the Sun's siblings using the same tools. If other stars formed in the same nebula 4.5 billion years ago, they should share similar chemical fingerprints. Their motions, rewound far enough, might point to a common birthplace. Finding them is harder than finding young siblings like those of the Pleiades. Over billions of years, stellar orbits are stirred and scrambled, and rotation rates converge, making age estimates less precise. But chemical tagging still holds promise. If we can identify even a few true siblings of the Sun and study their planetary systems, we gain a new mirror for our own history. Do those stars host planetary architectures like ours? Do they have belts of small bodies at similar distances? Answers to those questions would quietly reshape how typical we consider our own solar system to be, and by extension, how we think about the systems that might give birth to objects like 3I Atlas. The Pleiades story also whispers something about data itself. TESS was not built to find stellar families. Gaia was not launched to study the Seven Sisters. Large surveys mapping chemistry were not aimed specifically at extending this one cluster. Yet, by asking a new kind of question of existing data, how many stars out there share age, motion, and chemistry? Astronomers uncovered a structure that had been hiding in plain sight. That same approach could help with 3I Atlas. Old sky surveys, deep imaging campaigns, even photographic plates from decades ago may hold faint traces of where it was before we recognized it. Archival spectra might contain overlooked hints of similar objects. The right questions applied to the right combinations of data, can suddenly reveal that what we thought was a small, isolated thing is really part of something much larger. The shift from 7 stars to a 3,000-member, 2,000 light-year-wide family is more than just a pleasant astronomical footnote. It is a quiet reminder that our first impressions of the sky are often incomplete. The bright points we notice with our eyes are real, but they can be just the most visible knots in far grander patterns. 3I Atlas is a bright knot too in images, in spectra, in our attention. The ghost shells, the strange jets, the gasless green glow may all be hints that we are still only seeing its most obvious features, not the wider context it belongs to. Just as the Pleiades kept their true scale hidden until we combined rotation clocks, precise motions, and chemistry, the full story of this interstellar visitor may sit at the intersection of many kinds of data and many ways of looking, somewhere in a stellar nursery that may have long since dissolved under conditions we can only infer. 3I Atlas was formed. It has spent billions of years crossing the dark between stars, carrying whatever clues its structure and behavior can offer. Recognizing those clues may require the same humility we learned from the Pleiades, an acceptance that what seems familiar and simple at first glance can, under a deeper gaze, reveal an entire hidden family of truths behind it. Out beyond our own small system, about 40 light-years away, a faint red star has been quietly showing us just how harsh the universe can be. Astronomers have watched it unleash something we had only ever seen from our own sun before, a confirmed coronal mass ejection, a vast eruption of magnetized plasma hurled into space. This one was not gentle space weather. It raced outward at more than 5 million miles per hour, dense and energetic enough to strip the air off any unlucky planet in its way. This isn't a guess based on solar analogies. It's a direct, multi-wavelength detection. Radio telescopes caught a very specific kind of burst, a so-called Type II radio emission, the sound a shock wave makes when it plows through a star's outer atmosphere and starts disturbing the plasma there. X-ray instruments, watching at the same time, saw the hot, agitated gas flare and evolve. Together, those signals traced an eruption, charging through the star's corona and out into interplanetary space. There are many ways a star can flicker and flare, but that radio signature is the calling card of a true CME. The star itself is nothing like our sun in temperament. It's a red dwarf, smaller, cooler, dimmer, but far more restless. It spins roughly 20 times faster than the sun, and that rapid rotation whips its internal dynamo into a frenzy, building magnetic fields hundreds of times stronger than what we live under. Its surface is mottled with enormous star spots, dark magnetic knots where field lines punch out into space. Those field lines twist and tangle as the star rotates. Eventually, they reach a point where they can't bear the strain. They snap into new configurations, and in that snapping, stored magnetic energy turns into heat and motion. On our sun, that process gives us solar flares and CMEs, events strong enough to light auroras and, occasionally, to trouble our satellites and power grids. On this red dwarf, the same basic physics plays out at a much higher volume. The ejection we saw would sit in the top tiny fraction of 1% of solar CMEs for speed and density. If our own star launched something like that at Earth, it would be a civilization-scale event. For the red dwarf, it appears to be business as usual. Red dwarfs, especially young ones that haven't yet slowed their spin, are magnetically hyperactive. They flare often. They belch CMEs frequently. They drench their surroundings in X-rays, ultraviolet light, and storms of particles. If Earth orbited such a star at the same relative distance as our own habitable zone, our atmosphere would have a hard time surviving. Our surface, unshielded, would be constantly scoured. And red dwarfs are not rare curiosities. They are the rule. Roughly 7 out of 10 stars in the Milky Way are some flavor of red dwarf. Because they are small and dim, they're habitable zones. The shell around them, where liquid water could exist on a planet's surface, lie very close in, with planets circling in tight, quick orbits. That closeness makes those planets much easier for us to detect. They block a larger fraction of their little star's light when they transit, and they tug more noticeably on the star's motion. That is why so many of the Earth-size exoplanets you hear about live around red dwarfs. The numbers are real, but they tell only part of the story. A world can sit at just the right temperature and still be uninhabitable if it cannot keep hold of an atmosphere. A CME like the one just observed traveled at roughly 2,400 kilometers per second. For a planet hugging close to a red dwarf, that means the shock can cross the distance in hours. The impact compresses whatever magnetosphere the planet has, funnels particles into polar regions, heats the upper atmosphere until it begins to leak away into space. Do that not once, but over and over again for millions of years, and a thick, protective blanket of air can dwindle to a tenuous haze or vanish entirely, leaving bare rock under a harsh sky. Some worlds might endure. A strong intrinsic magnetic field can act as a shield, diverting much of the charged particle flow around the planet. Earth's liquid outer core, churning and rotating, powers such a dynamo. Mars, smaller and more quickly cooled, lost its global field long ago, and with it, much of its original atmosphere. The difference between a blue world and a rusted desert can come down to what is happening deep beneath the crust. But the conditions needed for a robust magnetic field are not automatic. A planet must be large enough to hold its internal heat, conductive enough to run a dynamo, and spinning fast enough to organize that convection. Close-in planets around red dwarfs are often tidally locked, always showing the same face to their star. That can slow rotation to match the orbit and potentially weaken the very dynamo they most need. The requirements for long-term magnetic protection are a narrow target, and many worlds will miss it. All of this gently complicates our dreams of life under red suns. Future telescopes are being designed to sniff out biosignatures, patterns of gases in exoplanet atmospheres that might hint at biology. Oxygen paired with methane, for example, or other combinations that shouldn't persist without some active, renewing source. Many of their first targets will be planets around red dwarfs, because those are the planets we can most easily study in detail. But if many of those worlds have already had their atmospheres stripped by relentless CMEs and flares, then their skies may be thin or gone. Life, if it exists there at all, might be buried under ice or rock, far from our view. The simple count of habitable zone planets becomes a much rougher, more fragile estimate of places where life could actually take hold and last. There are softer possibilities. Perhaps some red dwarfs age gracefully, spinning down and quieting their tempers, giving late-forming or late-healing worlds a better chance. Perhaps life thrives in subsurface oceans or deep crustal environments where atmospheres and stellar tantrums matter less. Perhaps there are rare systems where magnetic fields, orbital distances, and stellar moods all line up just right. The point is not to erase hope, but to recognize that temperature alone is not the whole story. The way this violent ejection was detected is its own quiet lesson. No single instrument saw everything. Low-frequency radio arrays listened for the long, drawn-out groan of the shock front, the Type 2 emission that tells you a CME is carving its way through plasma. X-ray telescopes watched the hot flare that came with it. Only by fitting those views together could astronomers say with confidence, here is a coronal mass ejection. Here is how fast it moved. Here is how dense it was. That kind of multi-wavelength listening is becoming our best strategy in a noisy universe. One band of light can lie, or at least mislead. Several together are harder to fool. In the background of all this, 3I Atlas keeps drifting through its own long story. The space between stars is not gentle either. It is cold, close to absolute zero. It is filled with high-energy particles that slowly damage whatever they pass through. Dust grains, tiny but fast, can hit like bullets. There is no atmosphere to soften impacts, no magnetosphere to turn storms aside, no warm daylight to heal. For a natural object, rock, metal, ice, under dust, surviving billions of years out there is already an impressive feat of durability. For anything more complex inside, whether a delicate internal structure or, in the more speculative imagination, a machine built for the journey, the challenge is harder still. Radiation degrades materials, thermal stresses crack them. Time itself works like a slow tide, wearing things down. Thinking about that little red dwarf tearing at its own planets puts 3I Atlas in a sharper frame. Whatever it is made of, whatever its origin, it has endured a galaxy that includes stars like that one. Stars that scorch their surroundings, regions bathed in storms, long stretches of deep cold and emptiness in between. To arrive here still active, still structured enough to launch jets and hold shells, is to carry the quiet proof of some remarkable resilience, whether born of nature or of something that once chose to build for such a journey. Each strange property of this object has some estimated probability of happening by chance in a natural comet. Some might be a few percent, others are fractions of a percent, or far smaller. On their own, any one of them could be waved away as unlikely, but not impossible. What makes 3I Atlas different is not one anomaly, it's the way many of them sit on top of one another. If these oddities are truly independent, the way we treat them in our models, their combined likelihood is found by multiplying their individual chances together. A 1 in 500 event stacked on top of a 1 in 1,000 event already gives you 1 in 500,000. Add several more low probability features and the number sinks rapidly beyond anything our intuition can comfortably hold. Take just a few of the better quantified examples. The alignment of 3I Atlas's incoming path so close to the ecliptic plane, the thin sheet where our planets orbit, has been estimated at only a few tenths of a percent if interstellar objects arrive from random directions. Its finely tuned arrival, passing near multiple planets while hiding behind the Sun from Earth's view at perihelion, drops into 1 in tens of thousands territory. Its nickel-rich, iron-poor chemistry appears well outside normal comet expectations, and its extreme polarization signature does not match any known cometary dust, including other interstellar visitors. If you treat even just those as independent and multiply their odds, you already slide into chances on the order of 1 in billions or trillions. And that informal stack does not yet include low water content for a supposed comet, an unusually fast and blue brightening near perihelion, non-gravitational acceleration without obvious fragmentation, persistent jets that hold their direction through rotation, or the ghost shells and dust behavior that refuse to fit standard models. By the time all 12 major anomalies are considered together, the implied natural by random chance probability shrinks into a realm of tiny numbers that feel more like a thought experiment than a serious expectation. Not literally zero, but close enough that simply shrugging and saying it's just a weird comet starts to feel less like caution and more like avoidance. This is where a different way of thinking becomes useful. Not pure frequentist odds, but Bayesian reasoning, the quiet bookkeeping of belief. In that view, you start with priors, your initial sense of how likely different explanations are before you see the detailed data. For anything in space, the natural object prior is very high. We know planets, comets, asteroids, interstellar rocks. We have never confirmed an artificial interstellar craft, so the artificial prior is low, as it should be. Then you let the evidence speak. For each new piece of data, you ask, how well does this observation fit under the natural hypothesis, and how well under the artificial one? If the behavior of 3I Atlas were entirely typical of comets, the natural hypothesis would be strongly reinforced, and the artificial one would fade further into the background. But that's not what is happening. Instead, one anomaly after another appears: alignment, timing, chemistry, jets, shells, spectra, and each one is a little awkward for ordinary comet. While many of them are exactly the sort of things you would at least consider plausible if you entertained engineered object as a possibility. Precise trajectory? A natural body can have one, but a guided craft would be expected to. Low water and unusual materials? Odd for a comet, less odd for something built. Jets that act like controlled thrust? Hard for sublimating ice. Easier to imagine as some form of propulsion or venting. Bayesian thinking does not flip the table. It gradually shifts weight. As more evidence piles up that is unlikely under one hypothesis and more comfortable under another, the balance of plausibility moves. A very low prior for artificial can be offset over time by a long string of observations that sit uneasily under natural, until the two no longer feel as far apart as they did at the beginning. None of this, by itself, proves anything. It simply says that, given what we currently see, it is no longer obvious that natural by default should be the only serious option on the table. This is where an old question slips in from the edges of the night. Fermi's puzzle: where is everybody? If technological civilizations are possible, and some are older than we are, then over the great age of the galaxy there has been time for at least a few to send probes to interesting stars. Those probes might not behave like loud emissaries. If their purpose is quiet reconnaissance, they might be designed to pass as much like ordinary debris as they can, saying no more than is needed. If we, today, were designing an interstellar probe meant to observe without overt interference, it would almost certainly not blink with radio beacons and neon signs. It might resemble a comet or asteroid on a carefully chosen path. It might carry protective dust layers that mimic natural regolith. Its activity might be subtle: small jets, slight course corrections, behaviors that are just strange enough to reward close attention, but not so blatant that any young civilization would be forced into a single interpretation. Under that lens, 3I Atlas's very ambiguity becomes interesting. It does not scream artificial in a way that would be immediately undeniable to every observer. Instead, it sits in a twilight zone, where careful analysis turns up a stack of improbable features, but each one can, just barely, be explained away with enough creativity and parameter tuning, it is easy to dismiss if you are uncomfortable with the implications. It is also easy, if you are looking for them, to see the outlines of design. Why would anyone choose ambiguity on purpose? Because an obvious, indisputable artifact would amount to abrupt first contact, whether anyone speaks or not. For a developing civilization, that could be profoundly destabilizing. Ambiguous evidence, by contrast, lets individual societies move at their own pace. Those ready to notice patterns and reconsider assumptions can do so. Those not ready can lean on natural explanations a while longer. Nothing is forced. It's exactly the kind of cautious, ethical strategy human thinkers have proposed for our own hypothetical probes. Be detectable to those who have the tools and the willingness to look closely, but not so blatant that you overwhelm cultures that are just beginning to understand their sky. Skeptics are right to say that extraordinary claims require extraordinary evidence. Calling an interstellar object artificial is one of the most extraordinary claims we could make. But there is a quieter, matching truth. A long series of ordinary improbabilities, all pointing in the same direction, can itself grow into something extraordinary. Intellectual honesty, here in the soft dark, does not demand that we choose a side now. It asks that we admit we do not yet know, that the data we have makes both unusually strange natural comet and deliberately designed visitor live possibilities. It asks us not to lock the door on one hypothesis simply because it feels unprecedented, nor to embrace it simply because it is dramatic. Tomorrow's sharper images and future measurements will feed back into this balance, nudging the scales one way or the other. For tonight, the stack of anomalies remains, like a quiet equation written across the sky, asking us gently but insistently to take it seriously. At some point, explanations that lean on one in quintillions luck start to feel less cautious and more like a way of avoiding a different, quieter step. Admitting that our assumptions about what can exist between the stars might be incomplete. It's easier to keep adding zeros to the denominator than to ask whether the category we're trying to fit 3i Atlas into is the wrong one. That's the background hum beneath whatever unfolds when the new images are shown. The presentation itself will be polished. The images will be clean, labeled, and accompanied by confident voices. They'll be framed with context and interpretation, designed to make sense to a wide audience and to reassure more than to disturb. What you likely will not see, at least at first, is the thing that matters most to people who want to test their own ideas: the raw data. When the high-rise camera collects frames, it doesn't produce pretty pictures. It produces FITS files, arrays of numbers with calibration data attached. Every pixel knows how long it was exposed, how the detector responds, what the background level was. Those files are where the real work happens. Turning them into images that humans can look at requires choices. How to scale brightness, how to stretch contrast, which parts of the dynamic range to emphasize, how aggressively to smooth out noise. None of that is inherently sinister. Astronomers do this all the time. Logarithmic or other non-linear stretches are used to cope with the huge difference between a blazing nucleus and a faint coma. Smoothing can suppress random speckles that would otherwise distract the eye. Edge enhancement techniques, like unsharp masking, can bring out subtle ridges and boundaries that might otherwise remain invisible. Used carefully, these tools reveal structure, but every choice nudges the story you see. A logarithmic stretch can make very bright and extremely bright regions look more similar than they are, hiding information about relative intensities that matter if you're trying to understand where most of the energy is really going. Heavy smoothing can wash away narrow jets or small asymmetries in the inner coma, merging them into a gentle blur. Aggressive edge enhancement can create halos and rims that look like real features but are really just artifacts of the processing. Without access to the underlying FITS data, you can't fully tell which is which. The field of view and exposure settings will shape what appears as well. High Rise was aimed at the nucleus and its immediate surroundings. It is superb at resolving small-scale surface details, but it is not necessarily tuned to capture faint, far-flung structures in the same shot. Ghost shells and detached rings that span hundreds of thousands of kilometers may fall outside the frame or be too subtle compared to the brightness of the core. Exposure chosen to protect the nucleus from saturation may simply clip away delicate halos. Color is another place where quiet limits matter. Ground-based images showing a green coma often combine filters or use broadband sensors in ways that, once calibrated, can highlight specific emissions. If High Rise uses only particular bands, or if its color products are composites not designed for precise spectroscopy, the green everyone has been talking about might not appear clearly or at all. The absence of that color in a press image wouldn't mean it wasn't there in reality. It would only reflect how the camera was used. Even something as simple as, "How big is it?" is not as straightforward as a caption makes it sound. Separating the solid nucleus from the surrounding coma in an image is a matter of thresholds and assumptions. The edge is not a crisp line. There's a bright core that gradually falls off into fuzz. Depending on where analysts decide the nucleus ends, they can get different diameters. The number presented on a slide will likely be a best estimate with uncertainties that might span kilometers. Even if the public version sounds precise, you will almost certainly see simulations, computer models of a comet-like body, spinning and venting, accompanied by lines or arrows showing how jets could form and how tails might appear from different angles. Those models are useful. They explore whether known physics can, in principle, reproduce certain patterns, but they are only as broad as their input assumptions. If the only mechanisms allowed in the code are sublimation of ice and passive gas dynamics, the model will dutifully search within that box. It will not stumble, by accident, on electromagnetic effects, active control, or anything that wasn't explicitly included at the start. When individual anomalies are addressed, they will likely be handled one by one. A sunward feature may be described as a projection effect. Odd chemistry may be tied to an unusual parent body. Low water content might be linked to long-term irradiation and depletion. Each explanation, taken alone, can sound plausible enough. What you are unlikely to hear is anyone stepping back and putting all 12 anomalies on one slide, asking what it means to rely on 12 separate, unusual, but possible stories at once. The language will matter. If speakers repeatedly call 3I Atlas a comet without qualification, that label does quiet work in the background, smuggling in a conclusion about nature even as the details are still in dispute. More neutral phrases like interstellar object leave space to let the evidence define the category. Listening for those labels and for how firmly they are used tells you something about the frame being set. Who is given a microphone matters too. If the panel is composed entirely of mission insiders and people already aligned with a particular interpretation, you are hearing a carefully harmonized choir. If independent voices, especially those who have raised questions, are included and allowed to disagree openly, that's a different signal. Most likely, The public event will lean heavily toward unity, a single, coherent story presented with confidence. Uncertainty itself may be smoothed over. Science, in practice, lives in phrases like, "so far as we know," within current limits. One possible explanation is press briefings, especially under political and public scrutiny, often prefer firmer verbs. Watch for how often you hear words like maybe and we don't know yet, versus is and must. The more polished the narrative, the easier it is to forget how much is still provisional. The images will almost certainly be beautiful. Seeing an interstellar object resolved down to tens of kilometers is, by itself, remarkable. Even if the surface looks unremarkable, a lumpy, cratered, dusty shape, it will teach us something about what billions of years in deep space do to matter. If, on the other hand, there are clean planes, repeating patterns, or any sort of geometry that refuses to fit ordinary erosion, the questions will grow louder, even if the official words stay calm. But it's important to remember that what you see in a 1-hour presentation is a curated first look, not the full story. The rest of the data will, eventually, make its way through archives and formal releases. Researchers will download FITS files, write their own code, argue over threshold choices, test different models. The real scientific conversation will unfold there, over months and years, in papers and preprints and conferences. Tomorrow is about framing. It is about giving the public something to hold on to, showing that NASA has delivered what was promised, and demonstrating, at least on the surface, that transparency is being honored after a long wait. That doesn't make it meaningless. It just means that silence, omission, and soft edges in the story are themselves part of the information. If you choose to watch, you can enjoy the wonder of seeing an interstellar visitor up close, and at the same time, keep an ear tuned for what isn't quite said. In a situation where the odds against just another comet have stretched into so many zeros, the gaps and hesitations in the official narrative may end up speaking almost as loudly as the images themselves. By now, the numbers and patterns around 3I Atlas have brought us to an edge that feels a little uncomfortable. We've circled the probabilities. We've watched how often unlikely has had to carry the weight of everything. And still, there's one quiet question hanging in the dark, the one most people would rather step around than look at directly. If 3I Atlas were artificial, what would we actually expect to see? It feels like a forbidden thought, like stepping out of the safe lane and into science fiction. But in truth, it's just another hypothesis. The only honest way to rule it out, or take it seriously, is to spell out what an interstellar probe would need, what it would look like under our instruments, and compare that picture to what we're observing now. Avoiding the question doesn't protect science. It only makes us clumsy at dealing with the data we already have. Think about the basic demands of a journey between stars. Something traveling for millions or billions of years would need to be very hard to kill. It has to survive radiation, micrometeorite hits, and long stretches of deep cold. It needs a way to manage heat when it passes near stars again. It needs power, either a store it can sip from after long dormancy, or some persistent source like radioisotopes or cleverly used starlight. It needs some form of propulsion for course corrections. It needs sensors, some way to store and process what it learns, and some way, eventually, to send that information home or on to others. And if the builders are cautious, it probably needs one more thing: a way to blend in, to look from a distance, like just one more harmless piece of debris. A thick, dusty outer layer would help with all of that at once: radiation shielding, impact protection, temperature control, and disguise. Coat a probe in regolith and ice. Let it spend ages sweeping up more dust as it travels, and by the time it reaches another star, its spectrum would look like what we see from 3I Atlas, a red, largely featureless continuum, with dust dominating the light. Any metal or complex structure underneath would be invisible to simple spectroscopy from the outside. It would be indistinguishable from a natural rock or comet core. Low water content would follow naturally if water isn't the main propellant or storage medium. Why carry large reservoirs of ice if you don't need them? A craft that uses other propellants, or that relies mostly on electric or nuclear power, might only have thin layers of frost picked up along the way. Heat it near a star, and a little water would boil off, but not enough to create the strong water signatures we expect in a classic comet. Unusual chemistry, like a dominance of nickel compared to iron, could arise from engineered alloys rather than primitive dust. Nickel-rich metals are favored in high-stress applications because they stay strong and resist corrosion. If surface erosion or exhaust reveals atoms from such materials, we would detect ratios that don't match standard cosmic abundances. The odd nickel signal from 3I Atlas, awkward for a natural comet, is quite ordinary if you imagine structural parts chosen for engineering reasons rather than born from a collapsing cloud. The jets, under this lens, stop being mysterious outgassing and become something more familiar. Thrust, intermittent plumes that turn on, stop, and resume a day later, look strange if you assume passive ice sublimation. They look much less strange if you imagine low-thrust maneuvers, timed burns, or systems that only fire when certain conditions are met. Jets that hold their direction even while the body rotates are hard to reconcile with random venting, but entirely expected if the flow passes through some kind of nozzle or gimbal, keeping the exhaust pointed where it needs to go regardless of how the main body is tumbling. The energy shortfall that plagues sublimation models vanishes if the true source of power is internal. A reactor, a long-lived battery, or some other store of energy can feed propulsion without relying solely on sunlight falling on a small patch of surface. Trajectory fine-tuning also slips into place. A natural interstellar object doesn't choose where to go. It follows whatever path gravity and chance gave it. An artificial one would be aimed and then trimmed along the way, passing close to Mars, Venus, and Jupiter, staying hidden behind the Sun from Earth during perihelion. These peculiar alignments feel like long odds under the natural hypothesis and like reasonable mission planning under the artificial one. If your goal is to sample multiple planets while avoiding the most curious nearby civilization at the moment of maximum activity, this is a geometry you might design. The resilience through inferred high mass loss and large non-gravitational acceleration, which seems so punishing for a fragile ice and dust body, also reads differently if you think like an engineer. We build probes and vehicles to survive the loads we plan to put on them. A structure designed from the inside out to handle thrust, shocks, and thermal swings would not necessarily fragment in situations that would tear a loose rubble pile apart. Even the ghost shells and concentric rings around 3I Atlas can be seen through this lens as exhaust patterns, thin shells of expelled material expanding away from a series of burns or structures shaped by symmetric thrusters. Their almost perfect circularity, their spacing, their growth at speeds of a few hundred meters per second all line up comfortably with low-thrust propellant flows, and the silent green glow with no obvious C2 lines, that too has a place in this picture. Ion engines and other electric propulsion systems can produce colored glows that are not dominated by the molecular bands we associate with comets. Excited ions and plasmas emit at characteristic wavelengths, but their signatures can look very different from the fluorescence of simple molecules like Cn or C2. A greenish coma without the usual comet gas fingerprints is a problem for natural models. It's not obviously a problem if we're seeing a kind of driven plasma rather than boiling ices. None of this is proof. It is a map of how the anomalies we've already listed could, in principle, be the expected footprint of something built rather than something born. It shows that the artificial hypothesis is not just wild imagination. It's a structured way to explain a set of observations that sit uneasily in our current natural categories. Of course, there are other possibilities. There could be natural processes we haven't yet modeled, weird outcomes of exotic formation environments we've never seen up close. The galaxy is old and varied. Sometimes, nature produces things that look engineered simply because both are solutions to the same physical constraints. Low probability is not zero probability. A 1 in quintillions comet that happens to mimic a probe is unlikely, but not logically impossible. The question then becomes, if 3I Atlas is artificial, what should we expect beyond what we've already seen? What predictions could turn this from a story into something we can test? We might expect patterns in its behavior that go beyond what random physics would produce, regularities in jet timing, for example, or course adjustments that happen on a schedule rather than only in response to solar heating. We might expect it to shy away from certain geometries, avoiding prolonged, close alignment with Earth-based observatories, while still choosing paths that give good views of other planets. We might look for subtle changes that suggest feedback, behavior that learns or adapts based on what the probe appears to encounter. A cautious design would also try very hard not to cross certain lines. No obvious radio beacons, no sudden, impossible maneuvers right in front of our best telescopes. Nothing that would force a young, noisy species like us to accept its artificial nature overnight. In a sense, success for such a mission might mean remaining forever ambiguous, clear enough for those ready to see, deniable enough for those who are not. If that sounds like an odd strategy, imagine designing first contact yourself. Great ships hanging over cities would be dramatic, but also terrifying. Perfect invisibility would keep everyone calm, but teach no one anything. Between those extremes lies a gentler path. Leave evidence that can be found by civilizations who have reached a certain level of curiosity and technical skill, and let them approach the truth slowly, in their own time. From that perspective, the way 3I Atlas sits in our debates, loudly anomalous to those poring over the data, almost invisible to the wider public, fits a little too well. But again, this is not a verdict. It is a reminder that the artificial question is not inherently unscientific. It can be framed in terms of requirements, predictions, and tests. It can be weighed with the same probabilistic tools we use for every other hypothesis. What makes it feel dangerous is not the method, it's the implication. Real science doesn't promise comfort. It doesn't forbid certain questions because they might invite ridicule or disrupt careers. It asks what the data demands that we ask, and it lets every plausible explanation take a turn under the light, no matter how strange it feels at first. The images and analyses yet to come will not, by themselves, close this chapter. They will sharpen some features, blur others, perhaps add new oddities or tidy away a few old ones. The deeper issue is how we choose to respond to what they show. Do we hold the artificial hypothesis at arm's length, simply because it sits outside our habits? Or do we allow it to stand in the same ring as every other model, tested and challenged and refined? In the end, 3I Atlas may turn out to be a natural object that simply pushed our understanding of comets and interstellar debris into new territory, or it may remain an ambiguous messenger, its true nature never fully settled. Or, just possibly, it may one day be recognized as the first quiet sign that we are not the only ones who have learned to cross the dark between stars. Whatever the truth, the way we handle the question says something about us. In this small, shared moment, with the night pressing gently at the windows of thought, the choice is simple: to look away because the possibilities are unsettling, or to keep looking softly and honestly and let the universe be as surprising as it really is.